Uniform distribution, part 2. In this video, we are going to do some examples and formula review for uniform distribution. Example 1. The thickness rho of a protective coating applied to a spaceship designed to work in harsh radioactive space conditions and uniformly distributed over the interval 10 to 30 microns. Find the mean, standard deviation, and cumulative distribution function of the thickness of the protective coating. Find also the probability that the coating is less than 25 microns thick. Since our function is uniformly distributed, we can apply the expectation of uniform distribution. We know that expectation of uniform random variable is a plus b over 2. And here a is our lower boundary 10 and b is our upper boundary 30. And 10 plus 30 divided by 2 is 20. So our average or expectation or mean is 20 micron. Now let's try to find standard deviation. Standard deviation, sigma, is the square root of the variance. And we know that variance of uniform random variable is b minus a, the quantity squared, divided by 12. So our standard deviation, which is square root of variance of x, will be 30 minus 10, the quantity squared, divided by 12. And if you perform this using your calculator, you're going to get 20 squared is 400 divided by 12 is 5.773 micron. Now let's find the cumulative distribution function. Before that, I would like to rewrite the PDF, the density function. The density function of uniform distribution is 1 over b minus a on the interval a comma b and 0 otherwise. Thus, our PDF density function will be 1 over 30 minus 10, which will be 1 over 20, supported on the interval 10, 30, and 0 otherwise. 1 over b minus a is at the same time the height of the function. Now let's go to cumulative distribution function, capital Fx of x. Let's use the variable t. So cumulative distribution function will be 0 if x is less than the lower boundary a. It will be x minus a over b minus a that we derived on part 1 of this video, supported on the interval, and it is 1 if x is greater than the upper boundary b. Thus, our cumulative distribution function is 0 if x is less than 10 micron, and it's going to be x minus 10 over 30 minus 10, which is 20, if x is in between 10 and 30, and it will be 1 if x is greater than 30. Now we're going to find the probability that the coating is less than 25 microns thick. So let's solve this problem graphically. Our uniform distribution function is supported on 10 and 30. And we have some height of the function here. We know that the height of the function is 1 over b minus a, which is going to be 1 over 30 minus 10, which is 1 over 20, is the height of the function. When x is less than 10, our function is 0. In the interval, it is 1 over b minus a, and if it is greater than 30, our function is 0 again. We are calculating the probability that x is less than or equal to 25. So that means we are going to calculate the area under this rectangle. The area of the rectangle is base times height. And the base is here 25 minus 10, which is going to be 15. And height is 1 over b minus a, which is 1 over 20. So the probability that x is less than or equal to 25 will be base times height, the area of this rectangle, which is going to be 15 over 20, which is going to be 3/4, which is 75%. So the probability that the coding is less than or equal to 25 micron is 75%. Let's go to second example. Suppose the time it takes a grade 1 student to get ready to go out for a school is between 5 to 15 minutes, inclusive. Let x be the time in minutes. It takes a grade 1 student to get ready to go out for school. Then x uniform will be 5, 15, supported from 5th minute to 15th minute. What is the probability that a randomly selected grade 1 student in at least 8 minutes? Find the probability that a different grade 1 student in more than 10 minutes, given that the child has already been preparing to go out for more than 7 minutes. This is uniform random variable. So the probability that randomly selected grade 1 student in at least 8 minutes will be graphically between 5 and 15 supported. That's our graph. It's going to be 0 if x is less than 5, and if x is greater than 15, our PDF is 0. And the height of the function is 1 over b minus a, which is going to be 1 over 15 minus 5, which is 1/10. What we are looking for is probability that x is at least 8 minutes. So x is greater than or equal to 8 minutes. At least 8 or greater than 8. So that is the area under this rectangle. And the area of this rectangle is base times height. Base is 15 minus 8, which is 7. And the height is 1/10. So 7 over 10 is 0.7. So 70%. Part B, we're going to find the probability that another student in more than 10 minutes, given that that student is already been preparing to go out for more than 7 minutes. So we know that the second student takes at least 7 minutes to get ready. And we are going to have new parameters for uniform distribution. Our new distribution will be supported from 7 to 15, because we know that it takes at least 7 minutes for him to get ready. And our PDF is 0 up to 7 and 0 greater than 15. We have some height of the function here, which is going to be new PDF 1 over BA, which is going to be 1 over 15 minus 7, which is going to be 1/8. Now we're going to calculate the probability that student takes more than 10 minutes to get ready. So that is going to be the area under this rectangle. So probability that x is greater than or equal to 10 will be the area of this rectangle, which is base times height. Base will be 15 minus 10, which is 5, and height is 1 over 8, which is 5/8. So this is the probability. Okay, what if the question was probability that the student gets ready less than 10 minutes, inclusive 10 minutes? Then that would be the area of this orange rectangle using our new parameters, given that the student has been already preparing more than 7 minutes. So this time we're going to calculate the area of this orange rectangle. Our base will be 10 minus 7, which is 3, and height will be still 1/8, and it would be 3/8. If you have realized that, this is the complement of that. So probability that x is less than 10 is equal to 1 minus probability that x is greater than 10. Now let's do formula review. Uniform random variable has two parameters, a, b. A is the lower boundary and b is the upper boundary that random variable is supported in this parameters. And a is the smallest and b is the largest parameter. So mean of uniform random variable is a plus b over 2. And the variance we have derived is b minus a, the quantity squared, over 12. And standard deviation is the square root of variance. So it would be square root of b minus a, the quantity squared, divided by 12. Our probability density function, little fx of t, is 1 over b minus a if x is in the, here our variable is t. If t is in between, if t is in between the interval a comma b, and 0 otherwise. 1 over b minus a is at the same time the height of the function. If you roughly sketch the uniform random variable, we have lower boundary a, upper boundary b, we have some height of the function. This height is 1 over b minus a, and our PDF is 0 if x is less than a, and our PDF is 0 again if x is greater than b, and in the interval a comma b, our PDF is 1 over b minus a uniformly. Our cumulative distribution function, capital Fx, is 0 if t is less than the lower boundary a. It is x minus a over b minus a if t is in the interval a comma b. We have derived this at part 1 by integrating the PDF, and it is 1 if t is greater than the upper boundary b. Area to the left. Let's roughly sketch this. We have some uniform random variable, let's call it AB, and roughly our graph is, PDF is like this, and we are looking for some value of C to the left. So that means that is the area of this rectangle. So probability that x is less than or equal to some value c is the area of this rectangle, which is base times height. We know that base is c minus a, and the height is always 1 over b minus a times 1 over b minus a. So probability that x is less than or equal to c is equal to c minus a over b minus a. Area to the right is, if we sketch it here, our height is 1 over b minus a, and we have some value c here. This time the area to the right of this rectangle. So probability that x is greater than or equal to c will be base times height, which is base is b minus c, and height is 1 over b minus a. If we were looking for the area between some interval, like we have lower boundary a, upper boundary b, our PDF is 0 up to here, our height is 1 over b minus a, after b it's going to be 0, 1 over b minus a, and let's say we're looking for probability that t is between c and d. So that's the area under this rectangle. So probability that x is between c and d is the area of that blue rectangle, which is d minus c, over the height, which is b minus a. So that's it for this random variable of the formula review and examples. I hope you benefited this video. Thank you for watching.